Hi, everyone. We're going to just give a minute for people to trickle in, and then we will get started.
Is there a public link for the YouTube spillover streaming thing?
We are. I just emailed it out to all the registrants, and we're about to put it on Twitter.
Oh, maybe that wasn't the ding that I got in my inbox.
All right. Well, it is 1:32 Central Time, so let's get going. Greetings, everybody. Welcome to our summer special session of the Electronic Health Economics Colloquium. I'm Ezra Goldberstein from the University of Minnesota, on behalf of the co-organizers, Shushan Donagulian, Sai Nikpei, and David Slusky, welcome. And just a few very quick announcements before I hand it over to our presenters today. The first is we know we have a really big crowd today, which is fantastic, and we suspect we have some people who are not EHEC regulars. So I just want to let you know we have a website, ehealthecon.org, and we have an email list that you can join on the website there if you want to be kept up to date on what we are doing. I also want to note quickly that we have two special sessions this summer, this being the first of the two, but then at the end of the summer and into the fall semester, we're going to resume our open call for papers for EHEC webinars. You can find information about the open call for papers on the EHEC website, again, ehealthecon.org. The deadline to submit papers is going to be July 14th. And one change that we're making is that we are going to have some special EHEC sessions that are specifically for grad student presentations coming up in the next round. So this will be open more broadly than it has been in the past. Again, go check out the details on the website and information on how to submit your paper. We'd love to have it. And last announcement is our second. So I said this is the first of our two summer special EHEC sessions. The next one is going to be July 14th. And we're going to post details about this shortly, but just to give you the teaser, it's going to be about getting started with R if you are a Stata user, which for people like me cannot learn this fast enough. So that's it for the announcements, and I am delighted to introduce Pedro Sant'Anna and Andrew Goodman-Bacon of Vanderbilt University and the Federal Reserve Bank of Minnesota, respectively. And we are delighted that they're going to be talking to us about the giant thing that seems to be looming for so many people about what in the world is going on with differences right now. So please, if you have questions, use the Q&A function, and we're going to be reserving about 15 minutes at the end for questions and answers. With such a big crowd, we know we can't get to everybody, but we'll do our best. So please, Bacon and Pedro, take it away. Thank you.
Well, thanks so much. Glad to be back at EHEC and talking to this large group of people. I know there's a lot of interest in this topic, and so I think we're going to try to aim today for people here who know a little bit about it or feel like on the periphery or wondering what's going on, and so maybe some folks on here are a lot more up to speed, which is fine, but I want to bring a lot of new people kind of on board with what's up with diff and diff when your treatment turns on at different times. So I am here as an applied researcher and a near constant diff and diff user. And what I'm going to do in my first half of the talk is tell you all about the potential pitfalls of using regressions to estimate your diff and diff models.
Yes. And hi, everybody. I'm Pedro Sant'Anna. I'm at Microsoft and at Vanderbilt, and I'm an econometrician. And in my half, I'm going to be spending most of my time explaining how to enforce that the underlying assumptions, difference in difference methods, are actually being imposed when you're choosing your estimation method. So Bacon, like, why don't you tell us a bit how you got into this, like, whole literature, how you started working on these topics?
Yeah, well, like I said, I mean, I'm an applied researcher, and my paper on this, just very thankful, I'm very grateful, it just came out in the Journal of Econometrics, not a journal I ever thought that I would publish a paper in. But this started for me when I was actually writing a paper in grad school at Martha Bailey on community health centers, which were funded in the 60s. They went to different counties at different times. And we had a bunch of really nice, promising two-way fixed effects results, nice looking event studies. We found that community health centers reduced mortality at the county level. So it came time to write the paper, and we had to say something about what our identifying variation was. And there was a sentence that said, we exploit variation in something. One version of the sentence said, we exploit variation in the timing of when health centers were established. And another version said, we exploit variation in where health centers were established. And I just got really interested in which was the right way to write that sentence. Then I started digging into what are these two-way fixed effects, or these fixed effects, diff and diff type regressions that we all were running. How do they really work? And then I'll say there's a second phase of me working in this area, which is when I came to Vanderbilt and got to talk to you, Pedro, every day, and learned a ton more about the econometrics underlying all this stuff. And so none of this would have ever been a paper if I couldn't have gone upstairs and complained to you about it. But I want to, so I'm going to like ruin the punchline here right at the beginning before I talk about some of the details. What I'm going to wind up saying today, let's see if I can get these slides to advance. There we go. I'm going to tell you I think we're going to say two things basically here, or at least I'm going to say two things. Staggered timing in a diff and diff, meaning you have a treatment that you're interested in, and it turns on at different times in different units. You know, states do things in different years, or hospitals implement some policy at different times, or counties run health centers, some in 1965 and some in 1969, et cetera. That type of variation can still be okay to identify treatment effects. That happens all the time in the world, and it can still work. But the real lesson, I think, of this new literature is that regressions are often not very good for estimating those effects. Just sticking them into a typical kind of linear regression, panel regression format really was hiding some potential problems. And so that's what I want you to keep in mind. I think Pedro will drive this home a lot more too. There's the identification side, like who are we comparing to who, and what do we need to believe for that to be a good idea? And there's the estimation side, which is like, how do we actually make those comparisons? And regressions introduce all sorts of weird problems that my work outlines. So, you know, back at the time when I was writing this initial sentence, I had a pretty simple and canonical idea in my mind of what diff and diff was and how it worked. So I would have a picture like this, for example. There's one group of units, group here, I call them group K, that get treated at a certain time. And I've just drawn this little theoretical example so that their outcomes immediately jump as soon as they get treated, and then they keep on going over time, just like normal. And then there's another group, group U, the untreated units. And you know, the classic way to think about diff and diff when you look at a picture like this is to say, well, here is the average outcome for the treatment group in the post period. Here is the average outcome for the treatment group in the pre-period. Here's the average outcome for the control group, like those untreated units that never get the treatment in the post period. And here's the outcome in the pre. And this defines two different differences, right? So there's how did outcomes change in the treatment group? How did they actually change? But of course, we're not sure that change itself, this would be a time series estimate. Is all of that change a causal effect? Well, we typically think not. There's other reasons outcomes grow or shrink over time. There's also a change in outcomes for the control group, and we don't think that they could have been affected by the policy at all because they didn't get it. They didn't get the policy, they didn't get the treatment, whatever. And so the idea of diff and diff, you know, simple diff and diff is to say, well, let's use the change in outcomes for the control group to approximate what would have happened to the treatment group had they not actually gotten treated. So, you know, you have the change that we actually saw for the treatment group, that's this big difference. The change that we actually saw for the control group, that's the little difference. And the gap between them is the difference of differences estimate. It's literally the difference of two differences. So the change in outcomes for the treatment group, post minus pre, minus the same change for the control group. Now, the nice thing, okay, so now this is all just like physically, what do you do? What do we typically do in the data when we say, I'd like to calculate a diff and diff coefficient? There's very convenient theoretical properties here. If you imagine if you write this equation in terms of potential outcomes, right? So now theoretical potential outcomes where Y1 is what happens to, what is the outcome for a given unit at a given time period in the state of the world where it was treated. And Y0 is what happened to a given unit at a given time period in the alternate state of the world where it was untreated. It turns out you can write down that simple diff and diff equation in this very convenient, elegant way where what it equals is a treatment effect parameter that we can understand and we can talk about and we can interpret the average treatment effect on treated units in the post period. That is a very well-defined causal object. And an identifying assumption. There's something else here that has to be true in order for us to get that nice causal interpretation of a simple kind of two-group, two-period diff and diff, which is the parallel trends assumption. We need the outcomes without treatment to have evolved in the same way for the treatment group and the control group. This, I think, is probably where a lot of us, how a lot of us learn diff and diff. I mean, if you learned it from essentially any econometrics textbook, any survey article, any labor paper, any sort of applied diff and diff paper, this is how they explain it. This is the ubiquitous explanation of what diff and diff is about. And we're gonna take this and see how it works. How do these types of conclusions, like what is the parameter that we get? What are the identifying assumptions? Those are the kind of questions that start to get a lot less clear when your treatment variable is more complicated, like when it turns on at different times, for example. So I want to just like ask Pedro a question here, because this is the kind of level of discussion here that really matters for interpreting the potential problems. And I didn't really pick up until I got a chance to talk to Pedro. So like, Pedro, what's attractive to you as an econometrician and a methods person about this type of formulation in a simple diff and diff?
Yeah, so what I like most about this simple formulation, it is that it's very explicit about what kind of identifying assumptions we are imposing to get, and what kind of parameter of interest we are actually recovering, right? So in this way, we know, like, oh, we are interested in the average treatment effect in post-treatment periods among those units who are actually treated. And to get that, we need to impose some kind of underlying parallel trend assumption that it makes clear the connection between what I am after, what I'm assuming, and actually what I'm recovering from the data, right? So it's like there is a clear link between all the moving parts that we all talk about when doing causal inference. And once we are aware of that, you can do this, like I call it difference and difference brute force or by hand, which is a simple comparison of means like Bacon just showed us. Or you can even do that in a simple regression models, which we are economists, we are addicted to regressions, and that really help us to leverage all that knowledge like that we have from regressions in other contexts to this so popular setup. So that's what I like it most.
Okay, so sometimes now that I get to talk to econometricians about this a lot, you often talk about imposing assumptions. Is that the same as just we make this assumption, we think this is true?
Yes. When I say impose, it's like, well, in order to recover the ATT, we have to kind of like, because it involves potential outcomes, right? And we're never going to observe Y0 for those units who are actually treated. So we have to somehow map those potential outcomes to observe outcomes, right? So when you're doing this link between what I would like to see with what I actually see, this missing part has to go away, right? So like this kind of imputation method, like imputation part has to go away. And whenever I say I'm imposing parallel trend assumption or imposing identifying assumption, it just means like, well, to recover what I want to recover, I'm making that assumption, and I have to justify it, right? It's just like, oh, I believe it, that's it. No, yeah, like you have to put some effort in justify why you believe that assumption is reasonable in that given context.
Got it. Okay, yeah, that makes sense. All right, so this is helpful, and this is helpful to me. And Pedro mentioned something that's really key to the way that we all start, this sort of path dependence for how we all started using staggered timing, which is that diff and diff number, the difference of those two differences, y bar treat post minus y bar treat pre, minus y bar control post minus y bar control pre. That is the exact number that you get out of this simple regression. You can get that algebraically exact number by regressing outcomes on a dummy for the treated units, a dummy for the post period, and that diff and diff is the coefficient on the interaction of treat times post. So, I mean, again, if you look in textbooks, like this is a key step because a regression, a difference in means doesn't give you standard error, but a regression does. A difference in means doesn't let you do other things that we're used to doing, like controlling for stuff, but a regression does. And so this is a tool that we've used all the time. So the beta that comes from the differences is the same as the beta that comes from the regression. But what I want to do is go right get out of like these theoretical explanations and talk about how this plays out in a very specific and ubiquitous example that I think is going to be incredibly familiar to 90% of the people on this call. And perhaps a shocking fraction of people here probably have run these regressions before. So let's talk about the first stage, the effect of the ACA Medicaid expansion on insurance coverage. So I'm showing you right now what the world was like for all of us in 2014. Okay, so we have a new version of the ACS. We can go download it. We can limit the sample to childless adults ages 25 to 64 with incomes under 300% of the federal poverty line. And we have now got this great sample going back to 2008 where we can measure insurance coverage. And in 2014, at the state of the world in 2014 is that we had a certain number of expansion states who went, usually pretty early in 2014, usually January 2014. And then we had about half the states, thanks to the Supreme Court, that didn't do that. And we have a diff and diff. This is great. This is a very simple looking diff and diff. The answer for how did the ACA affect insurance coverage as of 2014 was 5 percentage points. And this was a simple life to live in 2014. We all knew what to do. The estimator was very simple and it was very clear to show in levels. This was great. Then it turned 2015 and 2 more states expanded, or no, 3, Alaska, Indiana, and Pennsylvania expanded in 2015. So now we have 2 treatment groups. There's still the 2014 expanders. They're the same. Like, look at that solid black circles don't change. But now the non-expansion states are a little different. And there's this new treatment group, the 2015 expanders. Like, what do we do with them? And then fast forward even more. And the Medicaid expansion has gotten even more complicated because we have Louisiana and Montana expanded in 2016. So that's another treatment group. Maine and Virginia expanded in 2019. Last year, Idaho, Utah, and Nebraska expanded. I just don't happen to have 2020 data to put them on here. And then actually 2 weeks from now, Oklahoma claims that it is planning to expand Medicaid. So as we go forward, the variation in timing here is really starting to emerge. And you could imagine thinking farther into the future and wondering, well, which other states are going to switch? If you take the 80s example, maybe states will be induced to switch in the future. The variation is really changing. And what are we supposed to do? I mean, I have been in the position of looking at a graph like this where I break out my outcomes for the groups that are treated at different times and I plot them. And I just kind of wonder what's happening. Like, how should I be comparing these things? What should we do? Well, the answer has traditionally been to fix it in a regression, okay? So, and we've done this in a way that feels more flexible. Like we've said, all right, well, we were using, back in 2014, we were using a regression with a treatment dummy, a post dummy, and treatment time post. But now we don't know what post means. And now there's not just one treatment group, there's many treatment groups. So what we've done is replace the treatment dummy with unit fixed effects, unit dummies. That felt more general. We replaced the post dummy with a series of individual time period dummies that we could define for everybody. Again, that felt more general. And then you just include a dummy for whether or not the treatment is in place, if you want to get just a single diff coefficient. And if you go back to that 2x2 case, the treat times post specification is nested inside. It's a restriction on this general model. And I think our logic, our kind of panel regression type econometrics intuition was that more flexible specifications are better. They can handle more things. And this also allowed us to estimate the effect somehow. But the question here is that has been coming up recently in this new literature is, does this work? So before we talk about this, Pedro, I just want you to say something. What does it mean to you, like for applied people, for example, to say that something works? I mean, I think that what we feel often is that we have the data we have the policy variation we have. It might not be a huge sample. It might be a ton of variation. I think sometimes we feel restricted in what we can do. So what should we be thinking about at a stage like this for what will it mean for this approach to work or not?
Yeah, thanks, Bacon. That's a great question. I mean, that's a tricky question as well, because ex ante, it's hard to tell if something works or doesn't work. So me as an econometrician, I would say that one strategy is kind of work is that there is a clear map of what I am actually want to do with what I'm actually doing it. Right? So there is a map between our imposed assumptions to get a parameter of interest, right? And then this estimation strategy that I'm actually doing it is able to recover what I would hope that this estimation strategy would recover. Right? So what I think is important to stress that there is no the causal parameter effect, the causal effect. There are many different ways we can aggregate effects, right? So I think for me as an econometrician, an estimation procedure or a strategy works if we know what is coming out of that estimation technique, and we can give a clear interpretation about that. That's my take.
Yeah, that makes sense. I feel like it's easy to slip into the language. I've done it a million times where you're like, well, we're going to get the effect of this policy. I feel like I think I've learned now that type of language really rings alarm bells for you, right? Like the effect. I mean, we could be way more specific.
Yes, I mean, especially in this setup where I have many different groups, right? So people turn treatment on in different points in time. There are many different comparisons. There are many different questions we can actually ask, right? And I mean, it's not really clear what kind of question is more interesting than another. It's very context specific. So I mean, I think it's like being able to pin down what I'm actually want to ask my data, right? What is the kind of economic interpretation, economic question I want to ask? Makes things for me tons like cleaner.
Okay, good. Okay, so let's keep that in mind, because I think I'm going to try to tell you about now like the potential problems with running this regression. I'm going to do it as quick as I can so that everybody hopefully gets a better sense of like how and why things can go wrong. But I really want people to hear like Pedro talk about what you should do instead of this, because actually it's quite hopeful, you know. So we'll go down a little bit, we'll get into the dumps, and then Pedro will uplift you again at the end. So I'm gonna to go to a sort of simple example. And the approach that I use to fix this in any example really is just really to do algebra, right? So let's take, I just know how to use the Frischwald-Lavelle theorem where I partial out other covariates from the variable of interest. So the first thing I'm going to do to the treatment dummy is remove the unit means, DI. Step 2 is to remove the time means, so averages of this adjusted variable in each time period. That's what this second piece is. And then I've got a univariate regression coefficient. Then I know that beta hat diff and diff is this covariance right here. And I am certainly not going to do it right now in front of you, but doing a lot of algebra on this expression, you get the answer that I'm about to give you. But I want to show you in terms of a simplified case going back to the ACA. So here we're interested in the effect of the ACA Medicaid expansion on insurance rates on low-income childless adults. Let's just imagine that we were in a world with a simplified world with only 3 groups: non-expansion states, the 2014 early expanders, and the 2019 expansion states. So we have an untreated group, an early group, and a late group. And let's think about what are the simple kind of 2 group diff and diffs that we could pull out of a picture like this. This isn't quite as complicated as it really is, but this serves to show what's going on. First thing we could do is just forget about the 2019 expanders. We could just pretend like it was 2014 forever and compare the 2014 switchers, 2014 expansion states to the non-expansion states. And I mean, this is a beautiful looking picture, right? This looks really good. And this is one thing that we could do. Now we've dropped some information, so we could just flip it and forget about the 2014 expanders and instead compare the 2019 expanders to the non-expansion states. That would be another completely legitimate 2x2 diff and diff. So here we're comparing the early group to the untreated. Here we're comparing the late group to the untreated. Okay, and I'm kind of putting this like vertical line in between the pre and the post period for each treatment group, you know, that we're using. So that's 2. We've got 2 simple diff and diffs that we could calculate. There are actually 2 more. One would be to forget about all time periods in 2019 or later, and just compare the 2014 expanders as the treatment group to the 2019 expanders and use them as the control group, because prior to 2019, they are untreated. And so they are serving as controls here. That would be another totally legitimate 2x2 group pre-post treatment control type diff and diff we could calculate. And the real tricky thing, and actually the key to the problems with 2-way fixed effects, is that you could do the flip side of that too. And you could forget all data prior to 2014, and you could think about using the 2014 expanders in their post period as a control, because while they are treated, their treatment status isn't changing over that period of time. And so we could think about comparing the 2019 switchers who go from not expanded to expanded to the 2014 switchers who stay expanded the whole time. In principle, that could be an okay idea. And in fact, 2-way fixed effects is doing this. So in the simple 3-group example, these are the 4 2x2s you could pull out, 2x2 different diffs. And the main result of my work on this is that is exactly what OLS is doing. That's exactly what the two-way fixed effects approach does. It takes each of those comparisons. So the betas in this equation are each of those 2x2 comparisons that we just talked about, and it averages them together, okay? And the way it averages them together, I will talk about for a minute. It's a very typical OLS thing to do. I mean, Pedro will get into much more detail about which of these you might want to use and might not want to use, how you might want to average them. Those are really kind of nuanced questions that we can think clearly about ahead of time. OLS is imposing answers on us about which ones to use. The answer is all of them. How to weight them together. The answer turns out to be a combination of sample size, meaning when you compare the early group, the 2014 expanders to the non-expansion states, one part of the weight just depends on how big those groups are. That's pretty natural. That's not so bad. If groups are small, they don't get that much weight. The other really typical OLS thing, and I'm not going to really delve into these formulas, even though they're actually kind of simple in some ways. These are just asking, like, what is the variance of the treatment dummy in this little 2-group sample? Like, if we did two-way fixed effects on a data set that only contained the 2014 expanders and the non-expansion states, what would the variance of the adjusted treatment variable be? If we did a two-way fixed effects regression on a sample of 2014 expanders and 2019 expanders, restricting to the periods prior to 2019, if that was our little data set, what would the variance of the treatment dummy be? Those variances are also components here. And functionally, what happens is that if you are a unit that's treated close to the middle of the data set, you get a lot of weight. If you're a unit that's treated towards the end of the data set, you get relatively less weight. So that's basically what OLS is imposing. But it's quite nice to have this weighted average result, because that, to me, at least when I sort of figured this out, we went from having, I went from thinking about regression two-way fixed effects diff and diff in vague kind of econometrics like regression language, to now thinking about it in terms of very concrete building block language. Like, each of those betas is a function of y bars. Those are things I can calculate and touch in my data. The weights are functions of sample shares and, you know, what share of time periods different units spend under treatment, like variables that measure treatment timing. Those are also things I can calculate. And so it was really nice for me to get to this point in my work on this, is that it really demystified what was going on when I ran these regressions. So what does this mean? Like, what does this mean for two-way fixed effects? So I just told you that when you run a regression in this context, in this ACA first stage context, you put insurance rates on the left-hand side, you put state dummies on the right, you put year dummies on the right, and you put a dummy for whether the state has implemented Medicaid expansion. What does this mean? Well, the first thing is that I did it, and you get the answer is 7.4 percentage points. So when you run two-way fixed effects, you get a sort of first stage effect, a direct effect of the ACA on insurance coverage for low-income adults of 7.4 percentage points, which is a pretty big jump in insurance. So what does 0.074 mean? Again, the way I think about this is, well, it's a weighted average, and we should think hard, and Pedro will fix this. He'll tell you about this. What do the weights mean? Well, OLS, using a regression, is baking in a certain amount kind of weight, sample size, and those variance terms. Those might not be what you want. The variances might be upweighting certain groups that you don't think should be upweighted. They might be diminishing the influence of other groups that could be very important, or maybe they're not as important in your weighted average as you think they should be. Those are really deep questions that OLS doesn't let you choose, but Pedro's methods will let you choose that. They are a weighted average, though, of these simple 2x2 diff and diffs. The treated versus untreated. So that was 2014 versus non-expansion, 2019 versus non-expansion, and then in the real data, 2015 versus non-expansion, 2016 versus non-expansion. That's one type of comparison. There is the early versus late. So it's also, to some extent, OLS is comparing the 2014 expansion group relative to a control group made up of the 2019 expanders. That's one. And that last one is the late versus early. So using a group that switches compared to a group that has already switched. And the question should be, are each of those kind of comparisons valid comparisons? The answer is no. And again, Pedro will talk about how to fix this. So I'm going to show you briefly like how I use this result to visualize what's going on in two-way fixed effects. There is a stata command called make and decomp that will make these plots for you, but all I'm showing you here is I am using that weighted average. I'm calculating that weighted average for the entire ACA Medicaid expansion variation. So treatment groups are 2014, the 2015 switchers, the 2016 switchers, and the 2019 switchers. And then there's also this untreated group. And that generates a whole bunch of 2x2 diffs. Here I'm showing you the, I'm scattering the comparisons between a treatment group and a non-expansion group. Their diff and diff is on the y-axis. What's the value of their little 2x2 diff and diff? And their weight is on the x-axis. And you can see that this 2014 group gets a ton of weight. It's like 70% of the weight in these regressions is still on the 2014 expansion states and the non-expansion states. Those are the two largest groups, and they drive this coefficient a lot. The second set of things, this is all part of the same regression, are the early expanders versus late expanders. That's in these black X's. And so I've kind of labeled like what are the treatment groups here. You'll notice they all kind of get lower weight a little bit, but on average, their diff and diff is about the same number. Like the average diff and diff among the comparisons to untreated units was 0.075. The average among early versus late is 0.08. Now, the real kicker with the way two-way fixed effects works and the way these can go wrong is in terms of these later expanders versus early expanders. So here, I'm showing you here, I want to come back to this figure in a minute. The way you should think about these is that when treatment effects change over time, this particular type of comparison, a late switcher versus a control group made up of earlier switchers, this does not work anymore. So just think about this stylized example. This is like the last thing I'll talk about. Think about this stylized example where we have an early switching group, the gray line, and the treatment effect here for everybody is a positive number. It's a trend break. Treatment, when you get treated, your outcomes start to grow at a faster rate. This one's fine. You're going to get a positive number when you compare the gray line to the black line in this little middle period versus the pre. However, this second one is not fine anymore. In the second diff and diff, the black line is the treatment group, and you're comparing it to a control group that is the gray line. So you're saying we think that outcomes would have changed for the black line in the same way that the gray line is changing. And that is like evidently not true, because the whole reason that the gray line is changing differently in the post period is because it was treated. So that can't be a good estimate of what would have happened absent treatment, since it's driven by the treatment effect. And if you were to estimate this one in this little theoretical example, you would actually get a negative number for that second diff and diff, even though the treatment effects are all positive. So this is a very characteristic OLS thing. When you do that, and OLS is in fact doing that many times and averaging those numbers in, all those numbers they tend to be lower. You can see right here that some of them are negative. And if you were to just average together, what's the diff and diff among those type of comparisons, it's way smaller. Like these numbers are like 7.5, 8 percentage points. This is 2.7 percentage points, which is just what we would think if time varying treatment effects were biasing that type of thing. So
Bacon, just a second.
Yeah, go ahead.
Can you tell what is like being plotted in the y-axis? What's the unit of measure?
Yeah, these are in percentage points of insurance rate. So what this dot right here, so like, for example, this red line is the average of the dots weighted by, it's the average of the y-axis values weighted by the x-axis values. That's that weighted average result that my paper shows. That gives you back 0.074. That was the two-way fixed effects coefficient. But what we see from this dot right here, this was the highest weight dot. That was the 2014 expansion group versus the non-expansion states. That just says that if you only use those two comparisons, their effect would be about 8 percentage points. But down here, the 2015 expansion group, their effect was only about 3 percentage points. And so the y-axis here is the different values of the diff and diff coefficients themselves, the little 2x2 diff and diffs. And then the x-axis is what weight do they get in the regression. And when you combine those things, you get that two-way fixed effects number back. So this is what I wanted. This is all I wanted to get across to you today is like, how does the two-way fixed effects regression work, and what is it? Where do the problems come from? So I hope I'm going to kick it over to Pedro after I tell you that it's not the problem to use staggered timing. It's that the two-way fixed effects regression approach. These problems are worse when you're in this example we're showing you today, it's very familiar. I wanted to use it because I think we're all familiar with the policy variation, but it's not this does not suffer from very, very bad two-way fixed effects problems. The bias in this case is much worse when your treatment effects change a lot over time. These tend to settle out, so it's not too bad. It's much, much worse when your untreated control group is smaller. So if someday all states implemented this policy, there would be no untreated control group, and these problems would get worse and worse and worse. There's also this weird weighting issue that Pedro will talk about more in his half. Lastly, the other thing I want to say is this command bacon decomp, it's out there. You can use it. You might get asked to do it by a referee. I want to emphasize here that it doesn't fix any, my command here, that those plots don't fix any problems. They are diagnostics for talking about where the problems come from and how bad they could be. But as Pedro was about to say, there are other approaches other than use net regression that work. And the real upside here is that they can look good. They can be correct and give you a solid looking result when two-way fixed effects would have given you a bad looking result. So there's a lot of reason to be hopeful about what is on the horizon for how to approach this methodologically.
Oh, this is great. Bacon, before I take over, can you summarize what you think is the main contribution of your paper?
Yeah, I mean, to me, there's a lot of other work talking about some of these issues. So you also might, in that literature, you all might hear people talk about the negative weighting problem in two-way fixed effects. That is the same problem that I just talked about with the late versus early comparisons. So that's the same as the negative weighting problem. I think one of the biggest advantages of my paper is the way that it describes where these problems come from in two-way fixed effects. It talks about like how do we build up that two-way fixed effects estimate from the data, and it really digs into like why do these problems exist. But again, if you're in a referee type situation, I don't propose any fixes. That is Pedro's domain, and I will let him talk about that now.
Yes, perfect. So now it's my turn, right? So first I'd like to thank everybody, a big crowd over there that's spending some time listening to what Bacon and I have to say, right? So Bacon described essentially what is going on behind regression models, right? So you have a two-way fixed effects regression model, and it's like this regression is kind of like taking weights, comparing treated versus untreated, untreated versus already treated, like combining these weights and spitting out like a parameter. We call it beta hat, which many times they call, this is the quote unquote, the parameter of interest. But we know that like until like 3, 4, 5 years ago, there was not really clear understanding of what is going on behind the scenes of these beta hats from two-way fixed effects regressions. So the way I mean, and now we know as well, if we have treatment effect heterogeneity, which means like, well, different groups have different treatment effects. These treatment effects can evolve over time. That beta that is coming from two-way fixed effects does not really like represent easy to understand like causal parameter, right? So that's now what the main message. But the real question is, well, sure, I have been doing two-way fixed effect for so long, right? So this is not actually working the way I was hoping it was going to work. So what can I do? So this is more or less where I can come in, right? And before actually I describe what I can, my part, I would like to stress that my views on differences have been very much influenced, like while I was working with a couple of co-authors, but I would like to stress 2 co-authors here, which is Brantley Calloway, who is at the University of Georgia, and Jonathan Roth, who is currently at Microsoft, and he's moving to Brown in 1 month or so. Why I'm stressing these 2 co-authors? Because I have learned so much from them, right? Talking to them, and just discussing, writing papers together. And many people do not know this, but like actually Brent is the person who brought me to Difference and Difference World. So my first year when I was at Vanderbilt, I was talking to Brent a lot, right? And then Brent was like, well, I have his whole PhD thesis is on Difference and Differences. So talking to him, like, we said, well, let's start working together. Let's do something on Difference and Differences. So I have learned so much, right? So I'm very grateful for all his insights. And I have to stress, like, both him and Jonathan is like more recently working with him. They help shape my views on how to proceed. So having said that, the main content of this talk comes from the paper Colloquium and Sant'Anna, which came out in June of Econometrics 2020. And I would say that the main takeaway message over here is that we know that two-way fixed effect is not doing what we want. So how can I move on, right? Moving on, I would say, well, we should split this complicated task into 3 simpler tasks. What do I mean by that? We're going to first talk about identification, right? We're going to talk, which is analogous to Bacon's 2x2 DID results. We're going to talk about piece by piece on what kind of comparison we want to do it. When we stress what kind of assumptions we want to impose to validate those comparisons, right? And then we're going to say, well, in practice, we're going to have many of these 2x2 comparisons. We have seen a couple of minutes ago in the slides, like that's different, like healthcare expansions. We have different groups expanding different years, different points in time. So we have many of these 2x2. Then you say, well, we don't want to throw at you these 20, 30 different estimators, right? So what we're going to do, we're going to summarize these estimators in a way that is meaningful to your own application, right? This is what I call aggregation step. And once we're clear how I'm identifying each piece, how I'm aggregating each piece, then you're going to go to the data and say, well, fine, I know what I'm doing it. I have a parameter of interest. How can I map what I want to do with my data? How can I do estimation? And how can I do inference? Once we split the analysis in these 3 simple steps, you're going to see that the solution, like the fix for two-way fixed effects, are so simple. That is like, it cannot be simpler than this. It is in fact much simpler than regressions, because what we're doing is simple comparison of mix. So that's the main takeaway message. I mean, all the problems inherited in this modern difference and difference words is because we are relying on a single tool, right? Two-way fixed effects regression models to do many things for us, to do identification, aggregation, estimation, right? Me, at least myself as a control freak, I want to have like control each step separately and aggregate the way I want. So let me go first, right? So the main first point, let me talk about identification. What do I mean by that? Right, so the way I think about identification, it is, I ask myself, suppose I live in a world where data, it's infinite, right? I don't have any problem with sample size, right? I have huge data sets. In that situation, right, what is going to be my building block of my analysis? In a sense that, like, well, if I have no data limitations, what kind of question I want to answer with this given application? And in difference with staggered adoption, right, a reasonable starting point of the analysis is something that Brent and I, we call the ATTGT, right, which is have this formula over here, which is nothing more than the average treatment effect among units who are first treated in period G. So G here is a calendar time period. And I want to see the treatment effect of starting treatment at time G, right, versus never being treated. And you want to see this effect at calendar time T, right? So this is literally, say, well, if I am treated today, I want to see the effect of being treated today among all units who share the same starting treatment date as me, right? And I want to see this effect, instantaneous effect, which is today, this effect tomorrow, this effect the day after, and so on and so forth. So if data was no limitation, I believe this parameter is very interesting. It can highlight heterogeneity in different ways, has a very clear economic interpretation, right? And we say, well, if data was no problem, this is what I'm going to start over. So this is going to be my building block. But where is the catch here? The catch is that with this main building block, so units who are first treated in period G, I can observe their treated potential outcome, right? So I apologize for having different notations as Bacon, right? So Bacon used 1 and 0. I'm indexing potential outcomes by G here. So G, each treatment date, you have different potential outcomes. And if you are never treated, instead of writing as Y0, I'm going to write as Y infinity, right? So what I want to do is, like, I want to see the effect of everybody who shares the same starting treatment date as me, right? From switching treatment date from today versus never, right? And this is going to be my parameter of interest. But what's the catch? Well, among units who are actually treated for the first time period G, I do observe the first component, but the second component here, no matter how much data I have, it's never observable, right? Among units who are treated, I never observe untreated potential outcomes. So I'm gonna have to kind of find a way to replace this animal over here with something that is actually estimable from the data. How we do it? As in any causal problem, right? Any causal inference problem, how we solve this issue? Well, data is not helpful. So what we do, surprise, surprise, we impose assumptions. So the first assumption we're going to impose, it is about no anticipation, right? So this means that before treatment takes place, there is no treatment effect, right? So it doesn't matter what potential outcome you observe. So for in every single pre-treatment period, there is no treatment effect for each unit. This assumption is reasonable when treatments are not announced in advance, right? But it's not innocuous. So this can have a bite. So the first question when doing difference and difference that you have to ask yourself is like, well, do I believe in no anticipation? If I do believe in no anticipation, right? This is like check. If I don't believe in no anticipation, there are some ways to make this more flexible, which I'm not gonna go over in the talk due to time constraints, but this is important, right? So we have to be transparent on this aspect. So once I am done with no anticipation, suppose say, well, I believe this, that is no big deal, right? The second type of assumption is like, well, what is my comparison group, right? I want to compare treated units, and in order to impute those values for y infinity, I want to somehow, I have to find a way to replace it. So in those cases, how I'm going to do it? Here, I'm going to have many different options, right? In the sense, depending on the kind of comparison group I want to use, I'm going to impose a different parallel trends condition. The first option, it is to say, well, I want to use all units who are never treated, right, as my comparison group. So if I want to go in that sense, I'm going to impose a parallel trend assumption, like saying that, well, in the absence of treatment, so here I have y0 because I have already imposed, right, the no anticipation assumption, so that I can switch everything from infinity to 0. Right? So once I have imposed the no anticipation assumption, I can switch potential outcomes. And then what I'm going to do is like, well, in the absence of treatment, the average evolution of the outcome among cohort G, it is the same as the average evolution of the outcome among never treated units. If I believe on this, fine. But what's the deal here? In many applications, we either do not have a never treated group, right? So all units are eventually treated, right? So if in those situations, I can't use this assumption. Or in other situations, well, why I'm using those never treated? I can use a bigger group. For example, I can use all units who have not yet been exposed to treatment up to today as my comparison group. So in this case, we can adjust the notation a little bit further, right? The comparison group, and we can do this easily, right? So we can say, well, fine. I don't want to use the never treated. I want to use not yet treated units as my comparison group. So all the changes, it is choosing here the part my comparison group going to change. So this means I'm going to use all units who have not yet been exposed to treatment up to today. Once I make these assumptions, right, I'm comfortable with those assumptions, essentially the game is over. So I have imposed all identifying assumptions that I need. So how are we going to go from potential outcomes to estimates, right? So to this ATT function that only depends on observable data. This is the part that I love it about these new developments in the literature, because it's all about comparison of means, right? So if you see here, once I impose no anticipation and parallel trends based on never treated, to identify the average treatment effect among units who are in group G at time period T, I'm essentially back to the classical 2x2 DID, right? Because I have cohort G, cohort never treated, two groups. I have time period T and time period G-1, right? So which is so I have post, I have pre. So this essentially allows us to map everything back to the classical canonical setup.
So can I ask you a question about interpreting the way these these statements come when they come like from the method side. So we talked earlier about like imposing. So you said if we impose no anticipation and we impose parallel trends, this particular parallel trends, then this comparison on the right-hand side, which we can calculate, that equals a treatment effect. That's the magic here of like the assumptions combination. Like the assumptions tell you what you should physically do to get a meaningful answer. Is that right?
Yes, that's 100% on the point. So it's like the way I proceed is like this. I want to learn about the ATT for group G at time period T. All right, so learn about that, I have to impose assumptions. Once I impose those assumptions, I'm going to come up to this particular, on the right-hand side of this equation, I have something that depends only on realized outcomes, that is like, and all these expectations are estimable from the data. If I believe in those assumptions, we are good to go from this point.
If you're in a situation where like the ACA example, you've got like 5 treatment groups.
Makes sense?
Yeah. So what if we have like, you got like 5 treatment groups? You explained like the identifying assumption here for group G, little g. Like little g is 2014, right? Little g is 2016. Little g is 2019. It's one group at a time. If we believe that assumption, does it aggregate up to something so much bigger assumption? If we say like, oh yeah, it's 2014. Yes.
Okay. The more groups you have and the more time periods you have, the stronger the parallel trend becomes. Right. So the more post-treatment periods you have, right? You assume like so the evolution of the outcome in the long run, it evolves in parallel as well. So this is like as you have more groups and you have more time periods, parallel trends is becoming stronger and stronger.
I see. So if you say we have rich variation in timing, that sounds good, but it might make the assumptions harder to believe.
Yes, but this is the case if I do want to analyze group-specific treatment effects. Right, so this is what I'm doing right now. I'm zooming in to identify the ATT for group G at time period T, which is my mean. So this is going to be stronger. But at the end of the day, if I don't care much about this ATT-GT, but I care about a weighted average of these ATT-GTs, then the assumptions can be weakened.
Oh, that's great. Okay, so you're talking about what do you need to assume for each like building block to be good.
Yes.
So you're saying at the end, it's like whatever we build with it is what we want to work.
Yes. So the way I think is like, well, if every single piece of my building block works, the aggregate gonna work. But in some situations, the aggregate can work, but but I have mistakes in each piece, but these mistakes average out. And this is something I'm gonna talk in a second, right? So here, everything is back using the never treated to the 2x2 group. Well, if you don't want to do the 2x2 group, right? If you don't want to do the never treated as a comparison group, but you want to use the not yet treated as a comparison group, how you do it? Well, exactly the same. We are back to the 2x2 in the same way. I have cohort G, cohort not yet treated by time T, right? I have so treated, untreated, 2 groups. I have time period T, post, time period G-1, pre. So again, we are back to the simple comparison of means in the 2x2. So this is how we're gonna say, oh, if I have parallel trends for like each piece, depending on the comparison group we're imposing, we can back everything like to the simple 2x2 DID, and we have a good understanding on the 2x2, so we can move from there. Right, but what is the catch here? Well, if I have 10 groups or 4 groups in 10 time periods, I'm going to have so many of these ATT-GTs that's going to be complicated. So the way I think is like every ATT-GT is a piece of a Lego, right? So now that I have all the pieces of a Lego, I want to build something that is meaningful to me, to my own application, to my own research question, right? So this is what I call the second step, which is about aggregation, right? I want to summarize the effect of a policy, right, across groups, across time periods, in such a way that whatever this aggregation is doing it, I can explain to policymakers, to my fellow econometricians, or to my fellow applied researchers, what is the name of that parameter that it's coming out of this aggregation, right? So essentially, there are many different ways to aggregate, right? So it's essentially, you're going to say, well, I'm going to pick every group G, every time period T, right? I estimate every single 2x2 DID that respects my underlying assumptions, and I'm going to summarize them together. Right? So the way I'm going to give you the aggregation that I think it is most common, has attracted most empirical interest, which is related to event study dynamics. Right? So I want to see how the effects evolved since treatment took place. So this is what I mean. It's a kind of event study specification. So what I want to do is like, well, instead of having group and time specific effects, I want to have an effect that aggregates everybody who have been treated for a given amount of period, E. So how do I do that? Well, I get my ATTGTs. I relabel T to be G plus E. E is event time. So I'm gonna look for all post-treatment periods. So this is like post-treatment periods. And each group gonna have weights. They're proportional to the group size, right? So larger groups, so large cohorts gonna have more weights. Smaller cohorts gonna have smaller weights. So what the beauty of this procedure is like, well, the construction of this event study estimate, it is very clear, right? So we know what is coming out. We have full control of the weights over here. If you don't like these weights, you can change it. No big deal, right? You change it and you can do a different aggregation. And in Colloquium and Sant'Anna, we discussed these different aggregations as well. But for the sake of time, this is like what I'm going to talk about today in this aggregation. So third step, estimation and inference. This is very simple, right? All this discussion that I have done here, I have population expectations, right? This is like theoretical animals that we don't know then in most situations. But what can I do? Well, surprise, surprise. I don't know population expectations, but I do know their sample analogs. So estimation is going to be all about replacing population expectations by their sample analogs. I have simple comparison of means, right? So I can do all these comparisons, aggregate them together, and this is as good as you can get. The catch here is that, like, in practice, we don't really care about ATTGTs for a given G and a given T, right? We care about many of these ATTGTs or many different aggregations of these ATTGTs. So when you're doing inference about event studies, about different aggregation schemes, you're essentially running several hypothesis testing, right? So we know that you're incurring multiple testing problems, right? But the good news is that it's very easy to fix multiple testing problems in applications, right? So in Colloquium and Sant'Anna, we discussed this, like the solution, like in great detail. And essentially, all we have to do is, instead of using 1.96 as your critical value, you're going to use like bootstrap critical values to adjust for these multiple testing problems, and you're good to go. So going back now to illustrate if this matters or doesn't matter, right? So at the end of the day, the main method of Colloquium and Sant'Anna is about the path, right? So we are building this estimation procedure that is guaranteed to work regardless of additional assumption about treatment effect heterogeneity. So you don't have to a priori rule out treatment effect dynamics or a priori impose that treatment effect is the same across all groups, right, or all cohorts. So this is going to be like, well, we don't know at first, without seeing the data, we don't know if that's the case or not. So in the application of like using the same data as Bacon, we have like different groups, right? Here is very challenging to make inference about ATTGTs because we have 51 states, right? But some of these groups are very small. So in 2016, we have a group who has like 2. In 2017, have only 1 state. So apart from 2014, we have very few groups. So this means that making inference on ATTGT is going to be very complicated in practice, right? But still, you go to R, you use our DID command, you put all your instructions there, and then you write GGDID as our plotting command. This is what's going to spill out for you, which is like for each cohort, right? I have a different event study plot. So at least I have a very clear visualization of how treatment effects evolve over time for each given cohort.
Okay, this is a cool picture, and I think this like relates to the 2x2s that I showed, but it's beautiful and it's nice. I don't know how to use R. Maybe I should sign back into EHEC in a couple of weeks. What do I do?
Yes, I mean, that's the thing. So we have everything in R, but I mean, we also have a Stata implementation of the DID. I mean, it's not a native Stata implementation. So like Nick have written a wrapper around our R package that you can, if you're a Stata user, you can call that wrapper and run all of this behind the scenes in R and pull all those results to your Stata, right? And the link for that is unavailable on my webpage. So you can go there. I have a link in research. You can click Stata implementation. Everything's gonna come out in that way. And we are also currently working on a native Stata implementation where everything's gonna be like R. I mean, hopefully by August or early September, everything's gonna be good to go. Right, so I wanna stress like the results once you have aggregation schemes, right? So this is like doing many different ATTGTs, but for all cohorts bigger than 2014, we have problems with treatment group size. So inference, it is not reliable. This inference that we provide, it is not really reliable. So what we can do instead, we can aggregate all these ATTGTs into an event study plot, right? This is gonna use more data, more like groups. This is gonna be more reliable inference. So you can see here the effect. So comparing to the point estimated Bacon report, I think it was like 0.079. If you take the average of all post-treatment event studies here, you're gonna get something that is very similar, right? Which is not bad news. You look at pre-treatment trends, everything is kind of flat. And this plot is using the never treated as a comparison group. But you can do the same with all units who are not yet treated as a comparison group. And it's surprisingly very similar, right? Which again aligns with the message of Bacon, because when you do Bacon decomposition, almost all the weights are going to this like 2014 versus never expansion. And this is actually being reflected on this kind of event study decomposition aggregation that I'm reporting here. Finally, we can also do something that like, so I don't want to use those states who never are treated. I'm going to drop all never treated states from my data and only use variation treatment timing to construct the analysis. We got a slightly larger effects, but then we have some issues with pretrends, and these issues are non-negligible, right? And we have to be careful on this, right? On rely on pretest as well. So you don't want to go rely on pretest. What you want to do in principle is to kind of relax parallel trends, and hopefully you can use this very nice paper by Jonathan Roth and Ashish Rambadashan on doing sensitivity analysis on event studies in this case. So to wrap it up, because I'm over time for sure, right? In the paper with Callaway and Sant'Anna, like we have many different results, additional results on how to account for covariates, how to do double robust estimation, right? More things to be done there. I chose to present here the simplest case. Also, if you do believe that treatment adoption time, it is as good as random, right? Difference and difference procedure is going to be unbiased, right? But difference and difference procedure is going to leave a lot of money on the table, in the sense it's not exploiting all the assumptions behind this as good as random procedure. So John and I have worked on some extensions on how to get to milk all the power of the assumptions to get tighter confidence intervals in this paper, right? And just a final remark in self-advertisement, if you do not believe treatment time being as good as random, difference and difference procedures tend to be sensitive to functional form restrictions, right? And we formalize this result in Roth and Sant'Anna as well. But I mean, this is like kind of like the next agenda. Once you are, everything is okay with parallel trends, you want to do more, how can you do it? So this is a great place to stop. And I thank everybody for time and the attention.
So thank you so much, both of you. This is just fantastic. And so, you know, there have been a lot of questions coming in the Q&A that Bacon has been responding to. So, you know, it's I see 2:35 p.m. right now. Maybe we can have, like, you know, 10 or more minutes or so. If you, I don't know if there were any questions that you thought would be, or particularly important or illustrative that you want to respond to, sort of like over directly to everyone as opposed to just like the typed version? Defer to both of you about that.
Baker, you have been answering a lot of questions. I haven't taken a look at anything because I talk a lot.
Yeah,
So,
no, that's all right. I mean, I saw someone there asked about like, asked if your approach incorporated the 2014 versus 2019 comparisons that I talked about in my example. And I just want to like emphasize that, yeah, they do the good. So I was highlighting how two-way fixed effects will take the 2014 group and the 2019 group, and it'll calculate two things. 2014 versus 29 is the control, and 2019 versus 2014 is the control. The first one's good and it's in Pedro's method. The second one's bad and it's not in Pedro's method. So one reason to highlight this is that when you look out there in the literature, there are other new estimators that have been proposed. Sun and Abraham have one, Deshays, Martin, and Daufoy have one. I'm forgetting, there's several. And one thing that they all have in common, they differ on like the weighting sometimes and who they use as the controls, but the thing they all have in common is that they are working really hard to eliminate those bad comparisons that two-way fixed effects does make in.
yes, 100%. So I think the key of all these new like mini DID revolution, these new methods, doing it is like being very careful on how you pick your comparison group, right? I highlighted three different ways of picking it, right? So never treated, not yet treated, and not yet treated, excluding those like never treated. But there are infinitely many ways in between this case that you can also pick, right? So the difference between many of these methods is how they choose like the comparison group. And what is forbidden here, it is to use kind of like already treated units as a comparison group for other eventually treated units. That's the bad comparison that Bacon highlights.
So Pedro, Avigyan Sengupta asks about like when you're using the not yet treated and in a situation where every unit eventually does get treated, you can't get ATT for the last group. How does that affect interpretation and aggregation? Yeah,
so that does, there is a trade-off here. So if everybody is eventually treated, right, you're gonna, at the last period, everybody's treated. So there is no valid comparison group. So what you're gonna do, like in Colloquium and Sant'Anna, we're gonna kind of like, we're gonna go one period before, like the last treatment is actually, before the last group is treated. So I'm gonna get 80 TGTs for almost all periods, up to the last one. But that is tricky because that also induces some kind of compositional changes when you're doing event studies. But because the long run effects, in time periods, so in very long event time periods, my comparison group is much smaller, so I'm going to get less precise estimators. They're different. So what I recommend is to be careful on long run effects when you have you don't have an ever treated units, and be careful and try to impose balancing, right? So in event time, that would fix several of these issues on misalignment, on compositional changes.
Yeah. Okay. So here's one. This relates to something I wanted to highlight about our use of the ACA example that I think there's trade-offs there. But Ellie Baratz asks, how do you think about previous div research? Do you believe older results that don't address these issues? Is there potentially rich research data replicating and testing older results? Yeah, maybe. I think so. Just to be totally get to the root, of a lot of what's floating around out there about this. I think people are can be freaked out that their existing results won't hold up, and some might not. I don't know. I can't say. There are certainly methodological ways that we've now kind of learned about for existing two-way fixed effects coefficients published in journals being used to be misleading. That's possible. But the example we gave today is one where it was fine. It was fine in the ACA example because there was a large group of non-expansion states and there was a large group of 2014 expansion states. So even when you do two-way fixed effects right now, in this case, the ACA example is not giving you a two-way fixed effects coefficient that's very badly messed up by the problems. It's not that they're not there, it's just they don't get a lot of weight. So it's not like saying it's perfect and don't worry about it. It's just I'm just saying for the ACA example, this is one where it's not that big a deal. But if you were to go through and evaluate papers you've read or papers that have been published using these methods, prior to all this new work, the things that are most concerning are no untreated group. So all variation in timing, that's it. Very, very heterogeneous treatment effects over time. That's a big problem. And those are the things that are the most fishy, that can make 2FXX go the most wrong. The only other thing I'll say about like what papers we actually got published, I in some ways I have a feeling like there won't be a ton of overturning that happens, because the kind of bias you should expect from 2FXX will tend to make things, I would say, bias them not towards zero exactly. You can have a sign flip, but away from the sign of the true treatment effect. So in a way, it's more hopeful than that. Probably rather than overturning a lot of existing papers, I think probably what's going to happen is that there are questions that were seemingly put to bed because they gave garbage, noisy, meaningless mush answers that actually under the hood are fine if you use proper estimation approaches. And so maybe there's more of, rather than an overturning revolution, maybe there's more of like a resuscitating revolution.
And I also think that like it's okay, right? So if there are results that like going to flip, it's okay. That is no big deal. I mean, those methods were not available 5 years ago. We can't judge, look back and criticize other researchers. I mean, we have to take into account the technology was available back then. And I mean, I think that's totally fine. That's my take. It's like, because I think there's many people who are nervous. Oh, are my results going to change? Are things going to switch? I mean, my approach to this is like, well, you did the best you could, like using the technology available for you. So yeah, I mean, if it changes, so be it. I mean, we can update it and that's fine.
Okay, there's a couple questions about controls. And this is a thing that we've talked about a lot. Do you want to start off talking about what do you do? I mean, again, the reason that regressions were helpful and popular and like mostly harmless econometrics says as much. Cameron and Trivedi might, if I remember right, might say this, like they say it's really convenient to have a link to regressions because we can put control variables in regressions. What about that?
I can talk about this the whole next hour, right? So I would say like, first lesson from, this is a big pet peeve of mine. So the first one is like time varying controls. Those are dangerous. Those are many times misleading. And why is that? Because many times when you add time varying controls into your 2FX effects, I mean, those are post-treatment measured, right? So, I mean, I have like, I don't know, I have an X measured in 2020, but I was treated in 2015. Right, so in those cases, those covariates are highly likely to be affected either directly or indirectly by the treatment, right? And that's going to bias everything out. So first lesson for me is like time varying covariates. No matter how much you're used to do that, my pet peeve is like, don't do it, right? Use pre-treatment covariates. This is my interpretation, right? Think. Second remark along this line is like, what kind of covariate should you include in these procedures? I would say you should include covariates that you believe are important to validate your parallel trend assumption, right? So covariates here enter in a way to allow for covariate-specific trends. So if you believe, I don't know, like states in the Northeast would have evolved different than states in the South in the absence of Medicaid expansion, right? Then you want to add a region covariate to allow for region-specific trends. So the reason you want to add covariates into this like difference procedures is to allow for covariate-specific trends. And there are different ways of incorporating covariates into the analysis. So essentially, once you allow for covariates, you open a Pandora box because now you can add that via outcome regressions. You can add covariates using inverse probability weighting, or you can also add covariates using combination of the two, which is the so-called double robust methods. I am a big fan of double robust procedures because it gives you two shots to hit this one target, right? So I can get regression wrong, or I can get propensity score wrong, but as long as one of them is correct, I am good to go. So that's my favorite procedure, and that's all I have to say about covariates, because otherwise I'm going to keep talking about this forever. Bacon, what do you think about covariates? You have a different view than me. So
I have become more skeptical of them over time as a person who's stuck them in my fair share of regressions, partly because like when I go when I think through my style of doing algebra on a regression coefficient and trying to understand what does this regression coefficient mean, when I do that on a specification that also has a bunch of x's on the right-hand side, what I learn is that we're identifying off of the difference between actual treatment status and predicted treatment status, the way that those x's predict treatment. So like if some x's perfectly predicted treatment, it would soak up all that variation and you'd drop out. That's good, I think. I mean, if some x's are perfectly collinear with D, we can't be all that confident that we know a given coefficient really is the effect of D. But the problem is that then that introduces this weird new variation that I don't think any of us were prepared to stand up and defend, which is that two units can have very different effective treatment variables, even if they have the same actual treatment variable. Like two, I'm going to get the states wrong. I don't know, like Michigan and Idaho, not Idaho, I didn't do it. Michigan and I don't know, Massachusetts, let's say. I'm pretty sure they're both 2014 states. So they turn on in 2014. If they have really different predicted treatment statuses, they're going to get compared to one another. But we never said that one of them was a treatment and one of them was a control. We never planned to compare Michigan to Massachusetts. They're the same. They're in the same group. They're supposed to be getting compared to someone else. And so when you stick X's in, you're introducing all these weird comparisons that I don't think we thought we were using. And so I also now I like reweighting methods because I understand what it means to take the same averages, the same types of comparisons we used to make, 2014 versus non-expansion, and I know how to change the weights in the way that we create those means. So I understand that, and I understand how reweighting plugs into the kind of traditional econometrics arguments about what is the identifying assumption, what is the parameter that you get. I understand that, and so that's sort of where my mind has gone on covariates so far. Is that I trust a lot less when if I read a paper right now and it says this approach is good because we control for many, many, many things, I tend to disagree with that sentence. I would rather see that things work out okay when you don't control for many things. And then separately, you're welcome to show me that all of those X's are actually not correlated with your right-hand side variable if you use them as outcomes. So there, I particularly love a paper by Hannes Schwantz and Steve Pischke and Joan Pei, which is the greatest title ever, which is just called Poorly Measured Confounders Are Better on the Left-Hand Side Than the Right-Hand Side. It says it all. So put your X's on the left, tell me if they are correlated, and I putting them in my regressions less and less and less.
Yeah, and I agree. I mean, I think like if you really want to use covariates, I think difference and differences, if you want to use time varying covariates to control for time varying, like unobserved heterogeneity, difference and difference is not the right place, right? I think you should go to marginal structural models. People in the epidemiology and biostatistics have been doing this for a long time. Economists have been like lagging behind. I think those methods are more suitable for this type of like time varying heterogeneity than difference and difference per se.
All right. Well, I think that we're at time, or maybe even a little bit beyond time. So on behalf of everybody, thank you so much, Pedro, Sant'Anna, and Andrew Goodman-Bacon. This has been fantastic. Thank you to everyone in the audience for showing up. This has just been an amazing turnout. Again, if you want to know what's going on with EHEC, check out the website, ehealthecon.org. I know a bunch of people have asked. We will be posting the recording of this to our website, and stay tuned for our next session on July 14th, which will be about getting started with using R, which, as we learned today, will be a useful thing, and at least one of our presenters will likely be attending. So again, thank you so much to the presenters, and hope everyone is having a nice summer so far. Thanks, and take care. Bye.
Thank you, everybody.